previous class. So root and ratio tests, right? Okay. So you have some. Let's do the root test first. You have some infinite series, right? And does anyone remember what the root test is? Just to wake you up. What was the root test back from Calculus 2? Anyone remember? You look at the root, right? The nth root.
The absolute value
of the absolute value of the nth term. So consider the limit of the nth root of the size of the nth term, right, as m goes to infinity. And back in Calculus 2, you said, if this limit exists and it's smaller than 1, then you have convergence. If it's bigger than 1, you have divergence. And if it's equal to 1, then you don't know anything. Right? It could converge and it could diverge. Okay. But that was only if this limit existed. Okay. But now we'll see that we don't have to consider the limit. Instead, we consider the lim sup. And that always exists, right? The lim sup always exists, and so so we can apply this theorem. So if alpha is less than 1, then that tells you that the series converges. If alpha is bigger than 1, then the series diverges. Right? Then the corresponding series diverges, and otherwise you don't know. Okay, so if alpha equals 1, then you don't know. It could converge or it could diverge. And just like back in Calculus 2, the examples that show this are these two series, right? If you apply the root test to this guy, you see that the lim sup of the nth root of 1 over n, right? If you look at the nth root of 1 over n as n goes to infinity, this limit actually exists, right? And it's 1, right? And similarly here, this thing also is 1, right? But as we noted last time, this guy by the p series test diverges and this guy converges. So if it's 1, you don't know what's going to happen. Okay, could converge, it could diverge. You don't know. Okay. But if it's less than 1, then you have convergence, and if it's greater than 1, you have divergence. Okay. Let's look at this first thing. So suppose this alpha is less than 1. Okay. So this limit is less than 1. Then choose a beta such that so beta is between alpha and 1. Okay. So right here is 1. We've created this limit guy. This lim sup is alpha, and we choose some beta that's between. Okay. Now remember what we said about the lim sup. We had the characterization of the lim sup that says that we can find some number, and past that number, everybody's going to be less than beta, right? So there exists an n naught such that if n is bigger than n naught, all these guys, this thing in the 1 over n is less than beta. In other words, that what we see is that this thing is less than beta the n for all n bigger than that n naught. Okay, and that does it for us, right? We say we have convergence because all the terms are less than the terms of the tail end of a geometric series. Right, so by comparison test, summation a sub n converges. Remember, the comparison test said that if we had if we had that the moduli of some sequence was dominated by some sequence whose series converged, then this guy converged. Yes, Fernando.
Can we make a stronger claim such that the summation of the absolute value of A of n is convergent?
Yeah, in fact, that's true, right? Yeah, so in fact that's true, and that actually implies that the original series converges. But we haven't talked about that yet. So it is definitely stronger, but we haven't spoken about why it is stronger. Yeah, but but it is stronger. Okay. Okay. So and then the second one. Suppose that so if alpha is less than 1, then it converges, right? Then the series converges, right? If alpha is greater than 1, then we know there exists some subsequence n sub k root a sub n sub k that converges to alpha. Right? Because this thing is a subsequential, right? Alpha is a subsequential, is one of, the lim sup is a subsequential limit. Lim sup is a subsequential limit. Right? Right, which is bigger than 1. So there exists some k, right? So now we have 1 here, and we have alpha, and we have some subsequence that converges to alpha. And so we know that past some point, all of the guys in this subsequence are bigger than 1. Right? So there exists some k such that for k bigger than that time, all these guys are bigger than 1. All bigger than 1. Right? So that means that the size of the terms are all bigger than 1 past some point. Right? But that means that we fail to converge because of what? Because of the something test. The what?
The comparison test?
Not the comparison test, but the we've got these terms and they don't go down to 0. Right? It's the nth term test. Right? So by nth term test, or the nth term test, the original series must diverge. Because if it converges, all the moduli should go to 0. Okay. What is this, Sam?
Well, I guess on the test, would we be expected to be able to figure out, it's like doing all these steps and then eventually saying, like, by the end of the test, is that a solid?
Would this be a fair question on the test, is what you're saying?
Well,
This would not be a fair question on the test because I'm not going to ask anything about series.
Okay.
I'm not going to ask anything about series. So it'll go up through sequences only. Okay. So everybody's sitting back. I see pens going down. Okay. So yeah, this stuff is not going to be on the exam because you haven't worked on it. Right? You haven't done any homework or anything. So yeah. So the exam will cover only a few sequences. Okay, but say on the final exam, something like this would not be so strange. I mean, in particular, this first one would really, show that you understood what a lim sup was, right? I think this is a great example of how to use the lim sup, right? We don't have the limit, right? What would, having a limit would having a limit would just give us a lower bound here. But the thing is that we don't need a lower bound, right? All we need is that the terms are smaller than some number that's between alpha and 1, and that's exactly what the lim sup gives us. Okay. Okay, second old acquaintance, if not friend of yours, the ratio test. So again, we have some series, A sub n, and you look at the lim sup. So if the lim sup of, you recall, the ratio of successive terms, the size of successive terms, if that ratio is less than 1, then you have convergence. If the ratio exceeds or is equal to 1 for all n bigger than some n naught, then you have divergence. Okay, and of course number 3, you know, if actually there's no number 3. So not quite as neatly phrased as the root test. Okay. Let's think about number 2 first. Right. This, I think, should be clear. You see what happens, right? The ratio, if this happens, then an plus 1's modulus is bigger than the modulus of an, right, for all n past some n naught, right? And that's trouble, right? Because then the size doesn't go to 0, and so you diverge. Okay, so again by n term test, you have divergence. So that's easy. As for the first one, again, you think, you know, what if the limit actually equaled some number that was smaller than 1? Okay. I'm sorry, what if the ratio actually equaled some number smaller than 1? Right. That would say that you know, like A2 is equal to alpha times A1. It would also say that the size of A3 is alpha times the size of A2, which is alpha squared times the size of A1. Right? If this happened, again, you basically have a geometric series, right? So you'd have, you know, an, the size of an would be a to the n minus 1, alpha to the n minus 1 times the size of a1, right? And so we'd have a geometric series. Right? And if the alpha is smaller than 1, then this is going to converge.
Should we have like alpha n instead of alpha there? Because like it's not going to be alpha for each n case, right?
Say it again.
Should we have an alpha n instead of like alpha there?
Alpha n?
Because for like A2 and A3, it probably will be like another alpha.
No, I'm saying, what if we actually had equality,
So
we
it
actually had-
applies to each n case.
yeah, for every n, suppose we had, for every n, this actually equaled alpha. We don't have that, right? What we'd rather have is that the lim sup of this thing is some number alpha, and that number is less than 1. I'm saying, what if we actually had this? Okay, that this ratio equaled alpha. Okay, in that case, we'd have a geometric series, and we'd be done. Okay, and we don't have that, right? But the point of a limit is that we basically have that, right? We can get close enough to that this will be true, that our conclusion is true. Okay, right? The limit is going to be alpha. That means that we can make this ratio as close to alpha as we want, right? So we effectively have this. Okay, and so we'll have convergence. Okay, that's how you want to think about the limit. That you say, well, the limit allows me to pretend that this is true. Okay, and then you think, well, why would the result be true? Well, if this were actually true, then I have a geometric series. Done. Okay. Well, it's not really true, but it's close enough to true that I can get it. Okay. So that's how you want to think. Okay, so again, we don't have that, but so again, we don't have it, but we have that the lim sup of this ratio is some number smaller than 1. Right? That the lim sup is some number smaller than 1, right? And we play the same game. You say, okay, again, choose beta between alpha and 1, and by properties of lim sup, we know there exists some point in time such that past that point in time, right, all these guys are actually less than beta, right? Are actually less than beta, right? So for all n past that time, we have this thing is true, right? But that tells you that a n plus 1, right, is less than beta a sub n for all n bigger than n naught, right? But that tells you that, for example, a n plus 1 is less than. Let me just for convenience make this greater than equal. Okay. It makes no difference in the argument. We see that this is less than beta a sub n, and so on and so forth, right? What you see is that a n plus k is less than beta to the k a n, right? For all k bigger than 0. But what does it tell you? So you know that, right, the tail of a sub n is controlled by the tail of the geometric series, right? It is dominated by, so that's the point, by the comparison test. Summation a sub n converges. Okay, so that's the root test, and you see that in both cases the lim sup is enough, right? And that, yeah, Fernando.
Oh, I have a question about the second part.
Mm-hmm.
So for the ratio to be equal to 1,
Yeah.
yeah, I think that we don't have any conclusion.
That's right.
Yeah,
That's right.
so-
If this ratio equals 1, we don't know anything.
Uh-huh.
That's true.
Yeah, but why can't we have the greater than or equal to 1?
Well, the point is this: is because we're dealing with the limb soup. Okay. You see that? Okay. So here's the thing. So if the limb soup of this actually equals 1, then we don't get any result. And you can see that by example, right? The harmonic series and the sum of squares series, the reciprocals of squares series both have 1, and 1 converges and 1 diverges. Okay, you can use the same examples. You see that having equal to 1 doesn't give you any information. Okay. Now we're not talking about the limb soup anymore. We're just talking about the actual ratio of successive terms, right? If this thing equals 1, then that would tell us that after a certain point, the size remains the same,
Oh.
right? And then we don't go to 0, so we fail by nth term test again.
But okay.
Okay, and you notice
Yeah.
we're not talking about we're not talking about the limit anymore. Okay. Yeah.
And here
So-
the assumption is that a of n is not equal to 0. Because otherwise we cannot put that in the denominator.
Yes, that's true.
Yeah.
Yeah. Yeah.
Yeah.
Yeah. Thank you. Yeah. So it's, the the original ratio test back in Calc 2 is sort of more cleanly phrased than this, right? It says if the limit of this is less than 1, then you have convergence. If the limit of this is greater than 1, then you have divergence. Okay, but because we're talking about the limb soup, we can't phrase it so cleanly. But you can state something that's stronger, actually. Okay. Yeah, thank you. Okay. Okay, any other questions? Any other questions? In any case, let's go on to the next topic, which is extremely important, the notion of power series. Any series of the form summation c sub n z to the n from 0 to infinity is called a power series. Okay. Now, the c sub n are complex numbers, and generally called the coefficients. Right? And the z is a complex variable. You think of z as a variable, lying in the complex numbers. Okay. So this is basically like an infinite polynomial, right? Right. You've got c naught plus c1z plus c2z squared plus, but it goes on infinitely. Okay. So you've got something like this. And for different, as you vary your z, you get different values. If you vary your z, you get different values, and you're wondering, where does this make sense, right? Where does this make sense? Where does this series, for what z does this series converge? For what z does this series converge? Okay. And so what we do is we just use the root test to figure this out. Okay. So we say, okay, look at, right, the root test says we should consider the limb soup of the nth root of the absolute value of the nth term, right, we should look at this limit. Well, what is that? Well, that's the lim sup of, I'm just going to split it up here. Right? This times the modulus of z as n goes to infinity. Right? So I'm going to split this thing into the nth root of the first term times the nth root of the second term. Okay. So the root test says as long as this is smaller than 1, then then summation Cn Zn converges. Right? In other words, as long as modulus of z is smaller than 1 over the lim sup of the nth root, then we have convergence. And further, if z is bigger than that, then we have divergence. Okay. In other words, what is this saying? This is saying I'm sorry?
So modulus of z has to have to be less than
We want this thing to be smaller than 1 or bigger than 1, right? In other words, if z is less, if this times this is less than 1, then we have convergence. If this times this is greater than 1, we have divergence, right? So what is it saying? Let's call this thing R. Okay. It's saying that there's some, for every power series, there is some number, right? Such that if you look in the complex plane at the disk of that radius, right? If you look in the complex plane at the disk of that radius, then the power series converges inside that disk and it diverges outside that disk. Okay. So every every power series has what's called a radius of convergence, okay, in which it converges and outside of which it diverges. And then on the boundary, you don't know. It sort of depends on the series. So this R defined to be 1 over the lim sup of the nth root of the moduli of the nth coefficient is called the radius of convergence of the power series Cn z to the n. Okay. This is cool, right? This is what the root test gives us. Right? The existence of, that's I think that should be a little bit surprising, right? You have this polynomial. You have this infinite polynomial, and somebody says, well, where does this make sense? And it turns out that it always makes sense on a disk, right? It's not, there's some symmetry to the place, to the set of convergence, to the domain of convergence. Any questions about that? That's really important. Those of you who hope to take complex analysis in the near or far future will see this a lot in that class. So in that class, in complex analysis, it turns out that basically every function that's differentiable is expressible by a power series. And so you have to think about radii. You have to think about the disks of convergence. Okay. Some examples that will sort of clarify what happens on the boundary. What can happen on the boundary? What can the boundary? Okay. So So if we look at these guys, you see that here the coefficients are all 1, here the coefficients are all 1 over n, and here the coefficients are all 1 over n squared. Right? If we take the lim sup of the nth roots of those guys, then in each case we get 1. Right? The nth root of 1 is just 1. The nth root of 1 over n squared as n goes to infinity is 1. The nth root of 1 over n as n goes to infinity is also 1. Right? So these all have the same radii of convergence. Right? They all have the same radii. Right? All have radius 1. Okay. What happens if what happens on the boundary of that disk of radius 1? Well, what happens in this case? If you have you choose some point on the boundary of the disk, right? You choose some point whose radius is 1, and you take powers of it. Right? You take sums of those powers. What happens? Converges or diverges? Or you don't know? What? Guessing?
Shouldn't it diverge?
Why? By? Because? Yes, exactly.
This one.
Yeah, the nth term test?
Yes,
yeah.
that.
Nth term test, right? The size of the term is 1, right? The size of the modulus of the term is 1 to the n, namely 1. Right? So diverges at every point on the boundary. Right? Okay. Now how about this one? What do you think? Converges or diverges? You take some point on the boundary, and you look at the sum of z to the n over n squared.
It seems like it'll converge on every point.
Yeah, why?
Because you're going to get 1 over n squared.
Right. If you look at the size of it, right? If you look at the size of it, you get 1 over n squared, right? So you can compare this thing against the harmonic series, right? You compare it, right? We see that this thing is less than or equal to 1 over n squared, and we know that the sum of 1 over n squared converges, right? So by comparison test, this thing will converge no matter what point on the boundary we choose. So this thing converges at every point on the boundary by the comparison test. What about this last one? Can you tell me anything about this last one on the boundary? You can probably say one thing about it, right? You know that when we're at that guy, right, when we're here, right, when z equals 1, we've got sum of 1 over n, and we know that that guy diverges, right? That's a harmonic series. The p, remember p series yesterday, 1 over n to the p diverges if p is less than or equal. So we know that at least that this diverges at z equals 1, right? What we're going to see in a couple minutes, I hope, is that it converges everywhere else. So it converges at all other points on the boundary. In fact, it converges at all z equal 1 except at 1 itself. Now, the tool we're gonna need to use to get there is the following. So I'm just gonna erase the whole board. We'll get there, but it'll be kind of a roundabout path. So we're going to consider series that are products of two series. Okay. So, for example, the one we were just looking at, z to the z to the n over n. We'll break this up into 1 over n times z to the n. Okay, we'll think of this as two things. So what we're going to get is some results about convergence of these sorts of product series. Okay. Okay. And the main tool that we're going to use is the main tool we're going to use is something that we'll call partial summation formula. Okay. So here it is. You have two sequence. So let A sub n and B sub n the sequences. Okay. And let's notate A sub n, capital A sub n, as the partial sum from k equals 0 to n, where n is bigger than or equal to 0. And let's notate A minus 1 as 0. The sum of some sort of preceding sum. Then here's a claim, and this claim is not at all spectacular. It's just convenient. Okay. Here it is, that the sum of A sub n, B sub n from n equals p to q can be expressed in terms of these partial sums of A. Equals summation from n equals p to q minus 1 of A sub n times B sub n minus B sub n plus 1 plus capital A sub q B sub q minus capital A sub p minus 1 B sub p. So yeah, you should have sort of, you're right if you have sort of a bemused, confused expression on your face at this point. Like, okay, why? It'll be useful. Okay, it'll be useful. All this is basically a trivial, what do you want to call it? Matter of notation. Yeah, it's just you renotate this thing and you get this thing. Okay, let me show you how that happens. Okay, it's not at all interesting, but this will be useful. Okay, so let's look at this thing on the left-hand side. The sum from P to Q of A sub n, B sub n. And we rewrite this as, we rewrite the A sub n as capital A sub n minus capital A sub n minus 1. So he doesn't do something trivial. We'll do more trivial things, and then we'll end up with this thing on the bottom. Okay, so so the second trivial thing I'm going to do is just break this up. So the same range. I'm just distributing. Okay. The next trivial thing, maybe I should stop saying trivial, but they're all trivial. The next thing I'm going to do is I'm going to shift the index 1 up. Okay, so I'm going to make this A sub n, B sub n plus 1, right? That means I have to shift these guys down, so n goes from P minus 1 to Q minus 1. I'm adding 1 to the indices, so I'm subtracting 1 from the range of the index. Okay, and of course the next thing I'm going to do is combine them. Right? But I can't combine everybody, right? I can only get some of them, the guys who are common. So I can go from P up to Q minus 1, right? Those are the guys who are common to both sums, and then I have to throw on the guys who are not common to both sums, right? So I've got A sub n, B sub n minus B sub n plus 1, right? But then I've got the P minus 1 guy, right? And I've got the Q guy at the top, right? So I've got the Q guy at the top here, so I put that guy down. And I've got the P minus 1 guy here, so I put that guy down. P minus 1. Right. And that is the end. Okay. Should be shrugging like this. Like French people. Okay. Okay, everybody all right with that? Nothing happened. Right. It's amazing that we did all that and nothing happened. But okay, so okay, now we're going to use it. Okay, so now we're going to create this general theorem. Using this lemma, we'll create a general theorem, which is kind of useful. Actually, quite useful. I'm going to erase this. Okay, so so here it is. Here's the sort of the general theorem about these sorts of series. So general theorem about series that look like this. So let A sub n be a sequence whose sequence of partial sums is bounded. sequence of partial sums is bounded. It may, it doesn't have to, the series, the corresponding series may not even converge. Okay, so for example, a sub n could be -1, 1, -1, -1, -1, 1, -1, 1. That series, its partial sums are bounded, even, and if you try to sum it all, it does not converge. Okay? But that's fine. All we want is that the sequence of partial sums is bounded. Okay. Okay. Let B sub n be a sequence of non-negative numbers. Non-negative numbers. So non-negative real numbers that decrease. Right? So a sub n is bigger than or equal to a sub n plus 1 for all n, and such that the limit is 0. Okay. So you've got non-negative numbers and they decrease to 0. This should all be B's. Thank you. Thanks. Okay. If that happens, then the sum of the products converges. Okay. Okay. Let's see the proof of this. This may seem kind of strange at this point, but you'll see its application. We'll have multiple applications of it that show it's pretty useful. So we're going to prove this by the Cauchy criterion. Right. So fix some epsilon, and we want to we want to show that there's some time past which the difference of the magnitude of the partial tails is bounded, right? That's the Cauchy criterion for series, right? Right. So remember, right? We want to control the size of things that look like this, right? And from P to Q. We want n such that, right? We want to find some n such that, past that n, all the partial tails are bounded, right? All the sizes of the partial tails are bounded. So again, we're going to use the same notation. Let an be as before. Right? A sub n is the partial sum from k equals 0 to n. So as we did before in the partial summation formula. Okay, so here we go. Let M be the bound, right, of the sequence of partial sums. So let M be such that it's bigger than or equal to the size of A sub n for all n. Okay. Right, we said the sequence of partial sums is bounded. Let M be that bound. The bound for the sequence of partial sums. Okay. You'll see why we do this in a second. Choose n such that p bigger than n implies that the size of BP is smaller than epsilon over 2 times m. Okay. Yeah, that should be just pulled out of a hat at this point. But that's what we're gonna need. Okay. So maybe I'll just hide it for now, and you'll see that you'll see how it gets forced. Right? You'll see that we actually have to have that. Okay. So consider the size of summation a sub n b sub n as n goes from p to q. Well, we use the formula that we just created, right? We're trying to make this thing smaller than epsilon, right? We want to make this thing smaller than epsilon. Well, let's use the formula that we just created. This is the same thing as the sum from n equals p to q minus 1 of a sub n, b sub n minus b sub n plus 1 plus a q bq minus a p minus 1 bp. Okay, right, we just used the formula, right? The mysteriously boring formula. The tantalizingly boring formula. And now we're going to use the triangle inequality. So you say, okay, this is smaller than this. Right? But all these guys are smaller than m, so I'm going to replace them all by m. Right? They're all smaller than m. I have the sum from n equals p to q minus 1 of b sub n minus b sub n plus 1. I have bq, and I have bp. Right? I got rid of the absolute value signs on the b's because they were all non-negative, right? And I was able to get rid of it on this difference because the b's are decreasing, right? B sub n is bigger than b sub n minus 1, so this is positive, or at least non-negative, right? This is non-negative, this is non-negative, so I can get rid of all the absolute value signs. Okay, and then you see what happens. What happens? Well, here you get b sub p plus, minus b sub p plus 1, and then plus b sub p plus 1, minus b sub p plus 2, plus b sub p plus 3, minus b sub p plus 4, etc., etc. Right? So you get a telescoping sequence, right? You get a telescoping sequence, so you get m times the first term, b sub p, minus the last term, which is b sub q minus 1 plus 1, so that's b sub q, b sub q. And so we end up with 2b sub p times, 2b sub q times m, 2b sub p, sorry, times m. Now remember that we're trying to make this thing smaller than epsilon, and this is why we chose our n so that p bigger than n makes b sub p smaller than epsilon over 2m, right? So this thing will be smaller than epsilon, right? So let's put that back in here. Like you do all the work, and then you slide in, you say, okay, choose n such that p bigger than n implies that b sub p is smaller than epsilon over 2m. And so this thing is smaller than epsilon, and so you see that the series satisfies the Cauchy criterion, right? So converges by the Cauchy criterion. Okay, any questions? Questions? Okay, so this is a pretty cool general theorem that we're going to apply in a couple of cases. Any questions? Any questions on the proof? Right. All we did was rephrase the sum in terms of the partial sums of A, right? The assumption we had was that the sequence of partial sums was bounded, right? We rephrase this guy in terms of the partial sums of A, right? And see that the boundedness of the partial sums is exactly what we need to ensure the convergence of this series. Okay. Well, that plus ensuring that that these things are all non-negative, so that we can get rid of the absolute values. Okay. Yeah, sure.
Why did the summation turn into the BP minus BQ?
It collapsed, right? So you have, if you spell it out, it's b sub p minus b sub p plus 1 is the first term. And then the second term is when n is p plus 1, right? So you get b sub p plus 1 minus b sub p plus 2, right? And then you have b sub p plus 3 minus b sub p plus 4, plus minus plus minus plus minus, up until the last one, b sub q minus 1 plus b sub q, right? But you see that all these interior terms vanish, right? All these interior terms vanish. All these interior terms vanish in pairs, and you get left with the first and last ones. Actually, there should be one here. B sub p plus 2 minus b sub p plus 3. Right. So this one and this one cancel, right? This one and this one cancel, and so on and so forth. They vanish in pairs. Let me just give you one application, one quick application. Leibniz's theorem on alternating series. Right. If you have C sub n in a series such that they are alternating in sign, so C2m is less than or equal to 0, C2m plus 1 is greater than or equal to 0 for all m. To suppose that the limit is 0 as n goes to infinity, and suppose that the sizes are decreasing. Right. Then C sub n converges. And the point is that this is just an example of the general theorem, right? Proof: let a sub n be -1 to the n plus 1, and let b sub n be the size of c sub n. right? Then, right, this series is the product, right? Then C sub n is A sub n times B sub n, and we see that this is a sequence whose partial sums are bounded, and these guys are non-negative numbers decreasing to 0, right? And so that forces this alternating series to converge. So for example, right, if I look at -1 to the n times 1 over n from 1 to infinity, then this converges, right? Alternating series, and the terms decrease in magnitude. So you just apply the previous theorem, and it gives it. That's it for today. Yeah, I'd hope to get to why that other series converges at all points except for 1, but we'll do that after the exam.